Let us fall back to 500 BC. Heraclitus told us that Logos keeps the cosmos in harmony, moving all objects by a kind of law, by a sort of reason. This philosophically divided the world into two halves. To some, Logos is logic and natural law, and to others, Logos is logic and consciousness. This makes sense, as in order for us conscious beings to recognize facts of reality, and therefore form rules of logic to help us further identify other facts of reality, we necessarily have to have a consciousness capable of discovering facts, and thinking, and reasoning, etc. So, depending on your metaphysical basis of reality, e.g., a belief in a god or gods or scientific reasoning of Big Bang cosmology, will shape how you view the logos of the cosmos. Is it divine reason held in place with natural laws? Or is it natural, to which we have reasoned out some laws that aid our understanding? Aristotle was under the belief that logos was here on earth, as compared to his teacher Plato, that put logos in a divine creature that saw a cosmos of disorder and decided to organize it. Aristotle, given his observations of the nature of reality on earth, found that all objects of their own kind tended to find their way to their place in the order of all things, and that in order to move something required a constant force. This then was the first philosophical theory of gravity and inertia, that it was causal by the nature of the objects. Due to the fact that Aristotle was not aware of the concept of friction, this caused him, as it does to most people, to conclude that an object at rest remains at rest until you add a force to it, and that an object in motion will come to rest without a force constantly acting on it, or otherwise stated, an object in motion will only remain in motion while a force is applied to it. This led Aristotle to hold that objects will fall at different rates because of their mass, type, and the medium in which they are falling. Following Aristotle was the Christian theology and the Dark Ages they brought upon humanity for over a millennia, where the Logos became a humanoid figure with a plan to save humanity from the pain he's inflicting on them. On our first run through this timeline, we were focused on the stars in the celestial sphere as we passed from Aristotle to the Church, making those spheres levels of heaven, and the later shift in perspective that Earth was not at the center of those celestial spheres. However, this time we are exclusively focused on gravity, mass, and inertia, so we are going to take a detour to the Islamic world around the year 1000. Here we meet a prominent figure in philosophy and science, and whose accomplishments are typically passed off as being some European's accomplishment. The hero of this era goes by the name Ibn, or as he is known by the Latin corruption of his name, Avicenna. Ibn, in his philosophical encyclopedia, The Book of Healing, which is not a medical text, but rather a metaphorical healing of the soul through scientific experimentation and examination, provided us the philosophical thought experiment that Descartes would later utilize and get full credit for. Ibn, and 600 years later Descartes, constructs a thought experiment called the floating man. He speculated on what a man detached from objects of perception would be like. He's floating, without air pushing him or pressing against him. He cannot see or taste or touch or smell or hear anything. Can the man be self-aware of his existence in this floating space? Despite this topic historically swerving into ontology, epistemology, and psychology, this exact thought experiment will show up again with Einstein in 900 years. Both Ibn and Descartes conclude, quite illogically, that the man must be self-aware. He, according to them, thinks, and therefore he is, and he does so because God. Well, that will not be much use to us at the moment, but we will stick a pin in this floating man thought experiment and use it for something else later. What was most important from Ibn Sina at this time, however, was the conclusion he made about motion, which again Descartes would take 600 years later, but would not get the credit as Newton scooped it from Descartes in a like fashion. Ibn Sina disagreed with Aristotle, and rightfully so, and distinguished the difference between an object moving due to its inclination to its natural state and a force applied to an object, and that the inclination of motion on an object is in fact imparted to it by a force. That an object thrown by a man will have its energy of motion come from the logos of the man throwing it, and that the object will continue to move at that constant velocity forever or until acted upon by another force in the opposite direction. Essentially, inventing the conservation of momentum laws and the Newtonian laws of motion in the year 1000. Jump 500 years forward, and Copernicus is flipping the heavens around and changing how we view our place in the universe, which necessarily means questioning why things fall down, if the center of the Earth system is actually the Sun in the center of a solar system. If Earth is essentially in the celestial sphere of the Sun, which we can now call the planetary orbit, then why do rocks fall down if Earth is not at the center? Now, somehow, it is the rock that moves around the stationary fireball. We can, for the most part, just agree with Aristotle still, and say, well, fire goes up to naturally exist with the sun, and the rocks fall down to be with the earth. But in order to do that, we'd have to ignore Ibn Sina. That's fine, said the church. We will pretend he doesn't exist. In 1609, Kepler published his book called A New Astronomy, which includes the first two laws of planetary motion and states that the true theory of gravity rests upon the following axioms. Every corporeal substance, to the extent that it is corporeal, has been so made as to be suited to rest in every place in which it is put by itself, outside the orb of power of a kindred body. Gravity is a mutual corporeal disposition among kindred bodies to unite or join together. Thus, the earth attracts a stone much more than a stone seeks the earth. The magnetic faculty belongs to this order of things. Heavy bodies, most of all if we establish the earth in the center of the world, are not drawn towards the center of the world because it is the center of the world, but because it is the center of a kindred spherical body, namely the earth. Consequently, wherever the earth be established, or whithersoever it be carried by its animate faculty, heavy bodies are drawn to it. If two stones were set near one another in some place in the world outside the sphere of influence of a third kindred body, these stones, like two magnetic bodies, would come together in an intermediate place, each approaching the other by an interval proportional to the bulk of the other. Galileo tested experimentally the effects of this gravity by rolling balls down ramps. Galileo got a very small inclined ramp. The small incline meant that the ball was not going to be as affected by air resistance, which becomes more apparent the steeper the drop. Likewise, Galileo knew that if you dropped a ball from a short height from the ground, the impact the ball would make with the ground would be small, as compared to when you drop the ball from a high height. The higher the ball, up into a point, the harder it hits the ground, and therefore, something is happening here. Galileo did not have clocks, or cameras, or lasers, etc. So in order for Galileo to measure the rate of the balls as they rolled down the ramps, Galileo used water leaking at an equal rate from a vessel, and then measuring the weights of the water that was released in the amount of time the balls were rolling. Galileo found that the amount of weight in the cups was changing between certain intervals. For example, when he starts the ball at the very top, compared to starting at halfway. The water weight difference is not half, as you might expect. In fact, it would take about an equal amount of time for the ball to go down a quarter of the ramp as it would for it to go down the remaining 3/4. And likewise, if you start at the middle of the ramp, it takes about the same time to move a quarter of the way from half as it does from the other 3/4 of that half. It appears as if, in fact, there was a mathematical pattern to the motion, such that we can say that the distance it covers increases over time, aka it is speeding up. It is changing velocity over time. Galileo calculated that distance is equal to the square of the time, such that after 1 unit of time, the distance was 1 unit of length. After 2 units of time, the distance was 4 units. After 3 units, 9 units of distance, etc. Galileo was thus able to place a bell at a distance of 1, 4, 9, and 16 units from the starting point. And as the ball traveled the distance with acceleration, the bells each play at the same tempo. Galileo continued to drop balls of various weights and sizes down various ramps until he proved that 1. Distance is proportional to the square of time for everything, and 2. That objects retain their velocity in the absence of any impediments to their motion, i.e., has inertia. Galileo wrote, "Imagine any particle projected along a horizontal plane without friction. Then we know that this particle will move along this same plane with a motion which is uniform and perpetual, provided the plane has no limits." Some 40 years later, Robert Hooke told Newton about his hypothesis of orbital mechanics and the inverse square law of planetary motion. However, Hooke refused to show his proof and did not publish those results. But Newton did publish his mathematically derived mechanics of Kepler's laws of planetary motion, and then published the hypothesis of the inverse square law of universal gravity, making an enemy with Hooke that lasted the rest of Hooke's life. Newton's publication read, "I deduced that the forces which keep the planets in their orbs must be reciprocally as the squares of their distances from the centers about which they revolve, and thereby compared the force requisite to keep the moon in her orb with the force of gravity at the surface of the earth, and have found them to answer pretty nearly." End quote. The force of gravity is proportional to the mass of object 1 times the mass of object 2 divided by the distance from their centers squared. This is the universal law of gravitation, and it states that every particle attracts every other particle in the universe with a force that is proportional to the particles' masses and the distance between their centers of mass. This formula cannot, however, be used as an accurate equation until we find the gravitational constant, that rate of gravity which is true everywhere. G is the constant of proportionality attracting any two bodies from anywhere in the universe. The tension in the ether, if you will, the spring tensions of the ether of Hooke's, or the tension in the lines of force of Faraday, who historically here is yet to come. It was this confusing little constant of proportionality that made people skeptical of Newton, for he is essentially stating that there is an atom on a planet in the star system of Proxima Centauri which is attracted to an atom in you. In fact, to every atom in you. By what means was there to suppose this action at a distance, his colleagues scoffed. Newton, however, didn't really care about that, because he didn't need to postulate a hypothetical ether in order to account for his ideas. He had math, and the math worked every time. Well, not every time, but we will get back to that later. We needed to find this gravitational constant to make the calculations really accurate. Knowing the approximate mass of the sun and planets, and their distance between each other, provided great measures without the constant, but to predict things to the degree, to a second, would require more precision, and the fact of the matter is that not having a constant will always lead to failure. The constant must exist. Enter Henry Cavendish, who found a way to measure the gravitational constant. an elaborate setup which was a type of replica to Coulomb's torsion balance experiment. As the formulas are identical, so too is the experimental setup, kind of. A torsion balance holding two 350-pound lead balls, suspended opposite from each other, which had two smaller 2-pound balls positioned around the larger balls. The smaller ball's attraction with the larger ball was the main focus of the experiment. The use of two each is to balance on the torsion wire. As the smaller balls and larger balls mutually attract one another, this puts tension on the suspension string, which causes the suspension string to twist. The structure eventually comes to an equilibrium, where the torque on the wire can provide a measurable value of gravitational attraction. Cavendish's results were not as accurate as we have today, but compared to everyone else in 1797, he was the closest. And he found that the force on the wire was 1.74 times 10 to the negative 7 newtons, and therefore accounting for the masses of the balls and the distance between them, Cavendish found the value of G to be 6.74 times 10 to the negative 11 meters cubed per kilogram second squared. Today, we know that that value is 6.67408 times 10 to the negative 11 meters cubed per kilogram second squared. Two of the mathematical calculations of planetary motion did not work even after Cavendish found the universal constant G, and those were the orbits of Uranus and Mercury. In 1843, John Couch Adams and Urbain Jean-Joseph Leverrier independently predicted that there must be another planet, as the discrepancies between Kepler's laws and observations of Uranus were not making any sense. Unless something else was pulling on Uranus from outside the system. Given the orbital mechanics of Newton, if you assume another body must exist, and it does, then you will be able to predict when it is going to pass near other objects. By 1846, the planet Neptune had been discovered, when Leverrier sent his colleague the position in the sky to look, and that colleague, Godfrey Gale, found the planet right where Leverrier said it would be. Mercury was then the only object that Newton's laws could not fully account for. So many speculated another planet closer to the Sun, and they chose the name Vulcan, for the Roman god that forged the weapons of the other gods in his furnace under the island of Vulcano. This video is possible thanks to contributions to the Existence University Patreon by viewers like you. Thank you.